Welcome to this. This is our 24th lecture on the fundamentals of transport processes, where we were solving problems in unidirectional transport. I had posed for you a set of problems involving either mass or heat or momentum transfer. These problems were related to transport in one direction from an infinite surface into an infinite fluid. These could be posed for mass transfer, heat transfer or momentum transfer. In the case of mass transfer, it corresponds to having an infinite surface in which at initially the temperature everywhere is a constant, and at initial time instantaneously increase the temperature to a higher value. It corresponds to something like heating a surface, a container of liquid. We make the assumption of infinite fluid, and that approximation is valid only when the penetration depth of the temperature field due to this heating into the fluid is small compared to the system size. Okay. And we had posed exactly analogous problems in heat transfer and momentum transfer. Okay. In mass transfer and momentum transfer. Okay. So, mass transfer problem, you instantaneously change the concentration at the surface and then see how the concentration varies with time. And in momentum transfer, you instantaneously translate the bottom plate and see how the velocity varies with time. All of these cases we get exactly the same form of the equation. Diffusion equation, which contains one derivative in time and two derivatives in the spatial coordinate, and contains the dimensionless parameter, the diffusivity, whether it is for mass, momentum or energy, and it contains sources of mass or energy or the body forces in the case of momentum. These are all source densities, the increase per unit volume per unit time, or the body force is the force per unit volume per unit. Okay. So, that is the body force, and we use slightly different formulations for momentum transfer in comparison to mass and heat transfer, but we got the same equation. Okay. And then we solved this equation using a similarity solution for this problem, because there is a deficit of dimensional parameters for scaling the length and the time scales, and therefore, we were able to identify a similarity parameter, and we got expressions for this in terms of the similarity parameter for the temperature field, the fluxes, the total transport rates. And these solutions were exactly the same whether it was for mass, heat or momentum transfer. This might seem a rather idealized problem, but I had actually shown you an application where we can use this to get a correlation, and that was mass transfer from a falling film. In this case, rather than looking at the progression, the evolution in time, I look at the evolution for a parcel of fluid as it is translating downwards. Assumptions are close to the surface there is transport of mass, penetration depth of the mass into the film is much smaller than the thickness of the film, so that the film can be considered to be an infinite film. Also close to the surface, since we have a zero shear stress boundary condition, the velocity gradient is 0. Therefore, the velocity close to the surface is approximately a constant, because the slope is 0. Therefore, I can consider this to be a fluid that is moving at a constant velocity. And rather than solving it for a fluid moving past the reference frame at a constant velocity, I can sit in a reference frame moving with the fluid, since it is moving with a constant velocity, and in that reference frame, as time progresses, it is analogous to diffusion from a surface into an infinite film. And based upon this analogy, I had time is just equal to the spatial, the distance moved divided by the velocity, and based upon this I had just written down an analogous equation for the concentration field, and based upon that you can calculate the flux, you can calculate the average flux, integrate the flux over the height and divide by the length of the film, and from that average flux the Sherwood number, and we got the correlation. And I had also looked briefly at the conditions under which this approximation is valid. For real systems, these conditions are not very severe. So long as your film thickness, even if your length is of the order of 10 meters, so long as your film thickness is of the order of a millimeter or so, these approximations are still valid. That is because diffusion is such a slow process. The penetration depth is only of the order of 0.1 millimeters when the film has moved over a distance comparable to 10 meters, okay, for small molecule diffusion, okay, where the diffusion coefficient is of the order of 10 power minus 9. So, this is a very good approximation in liquids. Let us look at another problem here, and that problem corresponds to the decay of a pulse. Physically, what does it represent? I will first discuss this problem in one dimension, and then I will go on to 3 dimensions. Okay. So, I have this, okay, z coordinate perpendicular, okay, and the xy plane. Okay. This is an infinite fluid. Okay. The concentration C is equal to C infinity everywhere initially, okay, and at time t is equal to 0, I input a small pulse, okay, of the solute, okay, at z is equal to 0. Okay. I instantaneously put in a certain amount of mass of the solute at this location. In this case, the mass is per unit surface area, okay, in the xy plane. Okay. So, I do not define the concentration here, but rather the total amount of mass that is input is m per unit area, okay, is instantaneously inserted at this location. Okay. It is like generating a certain amount of mass instantaneously due to a reaction at this surface. Okay. So, if I look at the progression of the concentration with respect to time, okay, I have put a certain amount of mass into an infinitesimal thickness of fluid. Okay. So, if I look at the concentration, okay, variation in the z direction, okay, at different times, initially the concentration is 0 everywhere because I put the mass in at time t is equal to 0 only at this location. Okay. And at this location the concentration is very large. Okay. The concentration will basically go as the mass put in divided by the thickness, okay, because mass is m has been put in per unit area. The thickness of this pulse is infinitesimally small, so the concentration will be very large. Okay. As time progresses, this mass that has been put in is going to diffuse out. Okay. It is going to diffuse out, and as time progresses, I will get a profile that looks like this, okay, initially. Then as time further progresses, I will get a profile that looks like this. My apologies, this should be symmetric because this the system has symmetry between plus and minus z, right, because there is nothing that is distinguishing plus and minus z. So, the mass should concentration profile should actually be symmetric, okay, about z is equal to 0. Okay. I should note that since the total amount of mass is conserved, okay, as it spreads the height has to come down. Okay. So, it is not like the previous problem where we had a constant concentration at the surface. In this case the total mass is conserved. So, whatever is put in initially is what is going to diffuse. Okay. So, as time progresses, as the total amount of mass is conserved, okay, the width of the concentration profile will increase with time, the maximum will decrease with time. Okay. What is the conservation equation? It is the same equation that we had. I told you earlier while deriving the conservation equation that the conservation equation is derived for a volume within the fluid. Okay. Therefore, the conservation equation will just be partial C by partial T is equal to d square C by dz square. Okay. And this has to be solved subject to the boundary conditions. Okay. The concentration should be equal to 0 at z is equal to plus or minus infinity. Okay. As you go further and further away, okay, from this initial pulse, as z goes to plus or minus infinity, the material has not diffused there yet. So, the concentration has to be equal to 0. Okay. So, those are the boundary conditions for the concentration at plus and minus infinity. In this particular case, due to symmetry, you also know that dC by dz has to be equal to 0 at z is equal to 0, because the mass is being diffused symmetrically about z is equal to 0. Therefore, dC by dz has to be equal to 0. The slope has to be 0 at z is equal to 0. Okay. We do not have a boundary condition at a fixed boundary. Okay. However, we know that at t is equal to 0, C is equal to 0 for z not equal to 0. Okay. Whenever for any location apart from the location z is equal to 0, the concentration is equal to 0 at the initial time when you just injected this pulse in. Okay. At that initial time when you injected this pulse in, the concentration is equal to 0 everywhere else, okay, apart from z is equal to 0. Okay. However, we also have an integral condition. The total mass has to be conserved. Okay. That is, if I take the integral, okay, from minus infinity to infinity, okay, dz times C at any z and t, at any instant of time, I integrate the concentration over the entire z axis. Okay. This has to be equal to the total mass put in per unit area initially. Okay. This has to be equal to the total mass put in per unit area initially, which is equal to m. Okay, so, those are the three conditions that I have. In this particular case, since I have put in a pulse and it is diffusing in time, I have this integral condition. Okay. Now, how do we solve this problem? Once again, as in the case of the previous similarity solution, there are no length or time scales in the problem. Okay. There are no length or time scales in the problem. Therefore, I can write the equations in terms of one similarity variable. There is nothing that I can scale z with, because there is no length scale. It is an infinite fluid and the mass is diffusing in there. Similarly, there is no time scale. Okay. Therefore, I can define the similarity variable psi as before as z by root dt. Okay. How do I scale concentration? Now, that is where there is a difference between this and the previous problem. The condition that we have on the concentration is this total mass condition. Okay. The concentration condition does not state that the concentration is fixed at one particular location. Okay. If you look at the central location, for example, the concentration is actually decreasing with time. Okay. The maximum concentration is decreasing with time, the width of the pulse is increasing with time. Therefore, I cannot specify a concentration, okay, at any particular location. The concentration scaling has to come out of this balance condition. Okay. So, if I postulate that the concentration field is given by this function of z, okay, and if I re-express that in terms of psi, okay, you know that dz is equal to root dt times d psi. Okay. Therefore, in terms of psi, if the concentration field is now not individually a function of z and t, but only a function of psi, okay, my condition becomes minus infinity to infinity d psi root of dt, okay, into c of psi is equal to m. Okay. Therefore, this maximum concentration is actually decreasing with time. Okay. This maximum concentration by this scaling argument, if the total mass is fixed and the length scale for penetration is root of dt, the maximum concentration has to decrease as 1 over root dt, okay, which means that I can write this concentration. Okay. It is no longer just a function of psi, it should also be a function of t. Okay, so I can write this as m by root of dt times some dimensionless function of psi, okay, because the maximum concentration now has to decrease as 1 over root dt as the thickness of this is plume spreads proportional to root dt. Okay. So, this is the form of the expression that I have to use in the concentration balance equation in order to get a similarity solution. Note that the dimensional parameter here, okay, the dimensional parameter here is not a concentration, but rather a mass per unit area. Okay. So, to get a concentration field, okay, I have to scale that mass per unit area by a length scale, okay, to get a concentration. Okay. And therefore, this concentration is explicitly a function of psi and time. It can be written as m by root dt times some function of psi. Okay. So, that is the similarity transform that we have to use in this problem, and that comes out of the fact that concentration, that the total mass per unit area is conserved. So, let us go ahead and solve this problem. Okay. D square c, partial c by partial t is equal to d square c by dz square, okay, with c of psi t is equal to m by root dt, some function of psi. Okay. Therefore, partial c by partial t, okay, it has two terms here. There is a dependence of time in the prefactor, and there is a dependence of time through this function psi as well. Okay. So, the prefactor will basically give me minus m by root d t power 3 halves, right, f of, I should have a factor of 2 here, t power minus half gives me a factor of. Differentiation using chain rule. Okay. So, this is equal to minus m by 2 root d t power 3 halves f of psi, okay, plus m by root dt df by d psi into, okay, recall that psi is equal to z by root dt. That was our similarity variable. Okay. So, this becomes minus z by 2 root d t to the 3 halves. Okay. So, this is minus m by 2 root of dt into f of psi by t plus this term here is basically equal to psi by t. Okay. You can see that I have taken this factor of m by root dt out. Okay. I have taken this factor of m by root dt out and this factor of 2 out, and the negative sign also come out here. Okay. Therefore, I have z by root d times t to the 3 halves. Okay. Z by root dt is psi, okay, and since I have a t to the 3 halves in the denominator, I have to include that 1 over t over there. Okay. So, that is the left side of this equation. Okay. So, let us write that down here. 1 over t into, there is a factor of 2 there. Okay. So, that is the time derivative in this equation, okay, minus m by 2 root dt 1 over time times f of psi plus psi into df by d psi. What about the right side? dc partial c by partial z is equal to dc by d psi partial psi by partial z is equal to 1 by root of dt. Okay. So, this will be equal to m by root dt 1 by root dt df by d psi. And when I take a second derivative, I will get one more factor of 1 over root dt. Okay. So, when I take a second derivative, partial square c by partial z square is equal to so, let us put that as well in. Okay. So, this is equal to okay, by dt my apologies, it should be f here, okay, d square f by d psi square. Okay. So, that is the second derivative here. Okay, so, that is the second derivative. Okay. And that derivative of course has to be multiplied by the diffusion coefficient. That is the diffusion coefficient. Okay, that has to be multiplied by the diffusion coefficient. So, that is the equation that we have derived in terms of the similarity transform, the transformed variable. Okay. And you can very well see that in this case as well, this m by root dt will cancel out on both sides. Okay. This diffusion coefficient cancels out. Okay. And the time 1 over time cancels out on both sides. And I end up with an equation which is a function of psi alone. Okay. This equation is now in terms of the function f here, okay, but the resulting equation depends only upon psi. Okay. So, I can write this as d square f by d psi square is equal to 1 by 2 into f plus psi df by d psi. Okay, so, that is the equation for the function f. It is actually quite easy to solve this equation because this can be written as half d by d psi of psi f. Okay. Integrated once, you will get df by d psi is equal to half psi f plus a constant a. Now, this constant a you can determine from the boundary conditions. Okay. If you recall here, okay, if I write down the boundary conditions in terms of the function f, okay, as z goes to plus or minus infinity, okay, which corresponds to psi going to plus or minus infinity, okay, c is equal to 0. Okay, which means that m by root dt f is equal to 0, okay, because c is equal to m by root dt into this function f of psi. Okay. So, at z is equal to plus or minus infinity, this is equal to 0, which means that the function f has to be equal to 0. Okay. There is no surprise. I mean, as you go to plus or minus infinity, the concentration field has to go to 0. Therefore, this function f of psi has to go to 0. Okay. As you go to plus or minus infinity, this function f is equal to 0. The slope also has to be equal to 0, because if the function f goes to 0, the slope also has to be equal to 0. Okay. So, that means that at psi is equal to plus or minus infinity, f is equal to 0 and df by d psi is equal to 0. Okay. Because if you have 0 concentration, the slope is also 0. Okay. That means that this constant a has to be equal to 0, okay, in this particular case, from the boundary conditions at plus or minus infinity. Okay. Therefore, you can now integrate this once again. Okay. Psi f, which implies that log f is equal to psi square. I have missed a negative sign here, my apologies. Okay. If you recall, there is this negative sign here. Okay, so, this has to come in this equation. Okay. So, the negative sign has to come everywhere in this equation. It does not, of course, affect the constant a. Okay, so, this gives me log f is equal to minus psi square by 4 plus some constant b prime. Therefore, f is equal to b e power minus psi square by 4. Okay. Which is equal to b e power minus z square by 4 dt. So, that is the expression for the concentration field. Okay. This constant f is of course determined from the condition that integral minus infinity to infinity dz c is equal to m. Okay. And we had written c is equal to m by root dt, okay, times some function f of psi. That was our similarity transform. Okay. Therefore, if I convert now, I will get integral minus infinity to infinity dz c, okay, m by root dt is equal to m. Converting dz is equal to root of dt times d psi, okay, I will get m by root dt. Okay, I am sorry, there should be f over here, okay, times root dt integral minus infinity to infinity d psi times f is equal to m. Okay. And you can see that the m cancels out on both sides and root dt cancels out, and this condition basically states that this function has to be normalized. Integral minus infinity to infinity d psi f is equal to 1. Okay. And that determines the function b, okay, because okay, and from this you will find that do this integral, okay, b will be equal to 1 by 2 root pi. Okay. So, that is the normalization condition for this function, b is equal to 1 over 2 root pi, okay, because the integral from minus infinity to infinity, this term is just equal to 2 times root pi. Okay. This term, if you do the integral, it is a Gaussian integral, you cannot do it analytically, but if you do it numerically, you will find that it is equal to 2 times root pi. Therefore, expression for the concentration field C is equal to m by root dt, okay, times f. F is 1 by 2 root pi e power minus z square by 4 dt. Okay. I can also write this as m by 2 root of pi dt. So, this is the concentration field for a pulse input, okay, in which the initial amount of material put in per unit area was equal to m. Okay. In this, as I said, the maximum concentration decreases as 1 over square root of dt, and the width of the pulse increases proportional to root dt. Okay. We will look in a little more detail of the physics of this problem. I have got for you the mathematical solution. I will discuss a little bit about the physical solution of this problem in the next lecture and where it is applicable, okay, where this kind of a solution can be used. It turns out that it is very important both in turbulent dispersion as well as in dispersion in porous media, for example. Okay. And the dispersion coefficients are often calculated from profiles such as these. So, we will continue this discussion on the decay of a pulse in the next lecture. I will see you then.